Welcome to today's lecture on energy balances. In the last lecture, we looked at open and closed systems for single components and we performed some basic energy balance calculations. Today, we will continue with more fundamental aspects of energy balances, and for that we will now start with discussing energy balances for multiple component processes. When you have multiple components present in a process, then the specific enthalpy of the process itself will depend on the specific enthalpies of each of the components. The total specific enthalpy of the process or the system will be the summation of the specific enthalpies of the individual components, and the enthalpy can be calculated as the mass of the individual component times the enthalpy specific enthalpy of the individual component plus the mass of the second component times the specific enthalpy of the second component, and so on. And based on this, we would be able to calculate the total specific enthalpy or the total enthalpy of the system. So, this is measured and used for performing energy balance calculations in multiple component processes. When we do this, we are making an assumption, and this assumption is valid for ideal gas and liquid mixtures which have similar molecular structures, and we are also that is because we are assuming ideal solutions or ideal mixtures. So, based on this assumption, we have that the total enthalpy of the system is equal to the summation of the enthalpies of individual components at the same temperature and pressure. This is true only under ideal conditions. If there is a non-ideality where there can be interactions between the molecules which are present in the mixture, this assumption will not be valid. So, initially we will start with ideal mixtures and solutions to perform these calculations. Here is an example problem. You have a gas stream containing 60% ethane and 40% butane. This is to be heated from 150 Kelvin to 250 Kelvin at a pressure of 5 bar. You are asked to calculate the heat input per kilogram of the mixture, neglecting the potential and kinetic energy changes, using the enthalpy data that is given for ethane and butane and assuming ideal gas behavior. So, we have been given the specific enthalpy details for ethane under inlet conditions and outlet conditions and butane under inlet and outlet conditions. Using this, we have been asked to calculate the amount of heat that needs to be fed to the system per kilogram of the mixture. For performing this calculation, we have also been told to ignore kinetic and potential energies, and using this we will start with our calculations. The system we have is an open system because you have the mixture flowing in. So, we have been asked to calculate the amount of heat that needs to be supplied per kilogram. So, we will assume that the flow rate of the mixture which is entering into the heater is 1 kilogram per second. Using that basis, we will perform the calculations. We have been given that 60% is ethane and 40% is butane. So, let us start performing the calculations. So, this is an open system, which means the energy balance for this system would be delta H dot plus delta E k dot plus delta E p dot equals Q dot minus W s dot. So, for this system we have been asked to ignore kinetic and potential energies. So, these two will go to 0. There are actually no moving parts in the system like a piston or things like that. So, therefore, the shaft work would also be equal to 0. This means the equation is simplified as Q dot equals delta H dot. So, what we have is the amount of energy which needs to be supplied in the form of heat would be equal to the change in enthalpy which would be seen for the system. So, this delta H dot would be equal to sigma of Mi Hi cap in the outlet minus sigma of Mi Hi cap in the inlet. Now, let us calculate the outlet enthalpy. Outlet enthalpy would be equal to 0.6 kilograms of ethane times the delta H cap of ethane in the outlet plus 0.4 kilograms of butane times delta H cap of butane in the outlet. So, this value would be 0.6 times 973.3 plus 0.4 times 237. So, this would be the outlet enthalpy. Inlet enthalpy will be equal to 0.6 times delta H cap of ethane in the inlet plus 0.4 times delta H cap of butane in the inlet. So, this would be 0.6 times 314.3 plus 0.4 times 30. So, the difference between the outlet and the inlet enthalpies will be delta H dot, which would be outlet minus inlet, which is 478 kilojoules per kilogram. So, Q dot, which is equal to delta H dot, would also be equal to 478 kilojoules per kilogram. So, this would be the amount of heat which needs to be supplied to the system. Now that we have performed a simple energy balance calculation for a multiple component system, let us move on to understanding a fundamental aspect which is required for performing energy balances, which is thermodynamic tables. Thermodynamic information such as internal energy, enthalpy, specific volume, etc., can be provided in the form of tables in many handbooks. So, these tables are actually useful because you can get these values directly rather than having to calculate them every single time you perform these calculations. Such tables have been prepared for components which are very commonly used in chemical and biochemical industries. So, these tables show values such as enthalpies and other state properties and using a reference state. So, if you look at the appendix of B5 to B9 in Felder and Russo, which is one of the prescribed textbooks, you would find such thermodynamic tables. Perry's Chemical Engineering Handbook is another book which contains many such tables which provide all the thermodynamic data for commonly used substances. These tables list values which are the enthalpy or internal energy values in reference to a reference point. So, these values, as you remember, cannot be calculated as absolute values. Enthalpy and internal energy can be measured only as a relative value compared to a reference point. So, here some reference point would be used and the relative values would be given, and since we are always interested in finding the difference between one state to another, so taking a difference between the values from the table will eliminate the effect of such reference states which have been taken. So, thereby we can use these values directly while we perform these calculations. Even in the previous example problem, the enthalpy values which were given for butane and ethane must have been in reference to a reference point. It would have been relative to a reference point. So, we did not worry too much about what that reference point was, because it does not matter in the grand scheme of things, because we are only finding the difference and not really looking at absolute values. So, the reference point may or may not be listed in many of the tables. In the previous example, it was not listed. However, if you were to refer to the tables in Perry's handbook or in the Felder Russo, they usually have the reference states listed either directly or implicitly. So, you do not need to know the reference point for performing the calculations. So, here is a simple example problem to illustrate how such thermodynamic tables can be used. So, this is a very concise table that has been presented in front of you. Let us try to use this to perform energy balance calculations. The following table gives the data for saturated methyl chloride. You have the state of the methyl chloride, temperature of the methyl chloride, pressure, specific volume and enthalpy, all of them are listed in the table. First step is for you to identify the reference state, and the next is to identify the change in enthalpy and change in internal energy for a specific process, and the last one is to identify any assumptions if they were used. Okay, let us first start with the identifying the reference state. So, look at the data. So, you see that for liquid at minus 40 degree Fahrenheit and 6.878 psi, the specific volume is listed as 0.01553 feet cube per pound mass and the specific enthalpy is listed as 0. So, this implies that this particular condition would be the reference state used for this table. So, what we have is the specific enthalpy value of methyl chloride present as liquid at temperature of minus 40 degree Fahrenheit and pressure of 6.878 psi relative to a reference point is 0, which means these two values would have to be equal, implying this is the reference state. So, the reference state for this system would be liquid minus 40 degree Fahrenheit and 6.878 psi. So, that is the reference point. So, reference state is liquid minus 40 degree Fahrenheit and 6.878 psi. So, if you see, I would have mentioned the state, temperature and pressure to define a position of a state of the system. So, this gives you the complete definition of in which the system can exist. Now, moving on to the second part of the problem, we have been asked to calculate the change in specific enthalpy for the transition of saturated methyl chloride vapor from 50 degree Fahrenheit to 0 degree Fahrenheit. So, the first part of the problem asks us to identify the reference state in this table. If you look at the first row, it is liquid minus 40 degree Fahrenheit 6.878 psia, and for this particular condition you have a specific enthalpy value as 0. This implies that the specific enthalpy value entered here for this particular condition is relative to the reference state and that value is 0, implying this would be the reference state. So, therefore, the reference state for this problem would be liquid minus 40 degree Fahrenheit and 6.878 psia. So, this identifies the first problem. Now, for the second part of the problem, we would have to find the difference in specific enthalpy for the process where 50 degree Fahrenheit vapor is cooled to 0 degree Fahrenheit vapor. So, this means the initial condition is 50 degree Fahrenheit vapor and the final condition is 0 degree Fahrenheit vapor. So, the difference in specific enthalpy delta H cap will be final minus initial. So, this would be 196.23 minus 202.28 BTU per pound mass. So, this gives you a value of minus 6.05 BTU per pound mass. So, this is the change in specific enthalpy for the process where the vapor is cooled from 50 degree Fahrenheit to 0 degree Fahrenheit. We have also been asked to find the change in specific internal energy. So, this value is not directly available from the table. However, we can calculate specific internal energy as delta U cap would be equal to delta H cap minus delta of PV cap. So, using this, let us calculate delta U cap as minus 6.05, which is the value for delta H cap which we calculated, minus PV cap value for the final condition, which would be 18.9 times 4.969 minus initial value, which would be 51.99 times 1.920. This particular term, which is within the brackets, would have the units of PSIA times feet cube per pound mass, whereas the units for delta H cap were BTU per pound mass. So, this unit conversion needs to be done. For doing this, we can use the universal gas constants. The universal gas constant in terms of BTU is given as 1.987 BTU per pound mole degree Rankine. Similarly, universal gas constant in terms of PSIA can be given as 10.73 PSIA times feet cube divided by pound moles degree Rankine. Now, using these two values we can convert the value we have, which is PSIA feet cube per pound mass, into BTU per pound mass. Let us use these universal gas constant values to perform the calculations. So, delta U cap would be equal to delta H cap minus delta PV cap, which we wrote down as minus 6.05 BTU per pound mass minus 18.9 times 4.969 minus 51.99 times 1.920, the units being PSIA feet cube per pound mass. So, now we are converting this value into BTU using the universal gas constants, which would be 1.987 BTU per pound moles degree Rankine divided by 10.73 into pound moles degree Rankine divided by PSIA feet cube. So, the PSIA feet cube get cancelled, pound moles degree Rankine get cancelled. So, the units for this term now becomes BTU per pound mass. So, using this you can get the final value for delta U cap as minus 4.96 BTU per pound mass. So, this is the change in specific internal energy for the process of cooling this vapor from minus 50 degree Fahrenheit, from 50 degree Fahrenheit to 0 degree Fahrenheit. So, the third part of the question asks us to identify the assumption that has been made. The third part of the question asks us to identify the assumption that has been made. So, we have calculated specific enthalpy values without actually knowing the pressure of the final condition, which means we have assumed that the change in specific enthalpy was independent of pressure. So, this is a reasonable assumption to make for any small changes in pressure, because it is a gas and we can assume ideal gas behavior. Amongst thermodynamic tables, one of the most common thermodynamic tables which is used is the steam tables. So, steam tables are very commonly used because steam is involved in many chemical and biochemical processes, and because it is so commonly used, it is a waste of time to actually perform calculations to identify the change in enthalpies every single time. So, people have already built tables that can be used directly. So, what you see here is the phase diagram of water. So, this is a pressure versus temperature graph. At low pressures and high temperatures, water exists in the form of superheated steam or vapor. At low temperatures and high pressures, water exists as a solid, and at temperatures which are above a certain value and pressures which are above a certain value, water exists in terms of liquid. So, that is what you see here. So, the graph you have here, this line that you see is the solid vapor equilibrium, this line that you see is the liquid vapor equilibrium or the vapor liquid equilibrium, and this line you see is the solid liquid equilibrium. So, water exists as liquid in this region and it exists as solid in this region, and here it exists as superheated steam. So, this value you have here, this particular value would be the critical point, and this point is the state at which the difference between liquid and vapor becomes indistinguishable. At conditions above the critical point, you would have a gooey mess which you cannot distinguish between a liquid and a vapor. There is no definite change which actually converts it from a liquid to vapor, and this particular point is called as the triple point. So, triple point is the point in which you have all three states existing in equilibrium. You can have solid, liquid and vapor existing in equilibrium, and this point is called as the triple point. On these lines which I called as the solid vapor equilibrium or the vapor liquid equilibrium or the solid liquid equilibrium, two phases can actually exist. So, what would happen is, if you even have the slightest change in temperature or pressure, water would move towards one particular point. So, let me explain this from the graph. So, let us take this point which is on the solid vapor equilibrium. So, here at this particular pressure and temperature, you have water existing in the form of solid and vapor in equilibrium. So, if you were to change the temperature, let us say you increase the temperature, it will move towards superheated steam, whereas if you decrease the temperature, it will move towards a solid. Similarly, if you increase the pressure, it will move towards a solid phase, and if you decrease the pressure, it will move towards the vapor phase. So, what you see here is, by even slight changes in temperature or pressure, you can shift the equilibrium towards one direction. However, at that particular point which lies on that equilibrium curve, you would have both phases existing simultaneously. You would have saturated solid and saturated vapor existing at this point. Similarly, a point on this line would have a saturated vapor and saturated liquid existing simultaneously. Similarly, here at this, in this line, you would have saturated solid and liquid existing simultaneously. So, these are the equilibrium curves on which two phases can exist, and triple point is the equilibrium point where three phases can exist. Now that we have some fundamental understanding of what a phase diagram is, let us look at how the steam tables are built. Steam tables are actually built for saturated steams and for superheated steams. Saturated steam is the steam which exists in the vapor liquid equilibrium. So, what you see here is a saturated steam table which has been taken out of the Felder-Russo textbook. So, what we have here is the temperature based table. The first column that you see is the temperature. So, what is given there is a condition, the temperature condition in which the vapor liquid equilibrium exists, and the pressure is the corresponding pressure to that particular temperature at which the vapor liquid equilibrium can exist. So, let us take one particular example. For example, if we were to take 2 degrees Celsius and a pressure of 0.00705 bar, in that particular condition you have a vapor liquid equilibrium where you have temperature at 2 degrees Celsius and the pressure is the corresponding saturation pressure to that temperature. So, the first point which you see, the first data point you see is 0.01 degrees Celsius and pressure of 0.00611 bar. So, this is the triple point. What you see is the specific internal energy and specific enthalpy for this particular point have been represented as 0. So, this implies that the reference state which has been used is liquid water at triple point. The values for steam at triple point have been given as non-zero values. However, the value for water at the triple point is given as 0. This means liquid at triple point has been used as the reference state for this table. So, now let us look at each of the columns. Column 2 is the pressure which corresponds to the given temperature on the VLE curve. It is also called as the vapor pressure of the water at given temperature. So, column 3 represents the specific volume in terms of for the water which exists in the vapor liquid equilibrium or the liquid water which exists, and the steam which exists is the given in the column 4. You have column 5 and 6 giving the specific internal energies of saturated liquid water and saturated steam at given temperatures. So, these values are relative to the reference state which is the liquid water at the triple point. Column 7 through 9 represent the specific enthalpies. Column 7 is the specific enthalpy of saturated liquid water and column 9 is the specific enthalpy of saturated steam. Column 8 is actually the difference between the two, representing the heat of vaporization at that particular condition. Once this particular amount of heat is supplied, the water liquid will completely be converted to water vapor. So, that is what this heat of vaporization, evaporation or heat of vaporization represents. You can also have a similar table existing in terms of pressure. So, what you see here is the first column is the pressure, and for that particular pressure you have a corresponding temperature which is given, and rest of the values are similar to the previous table. Other than the saturated steam tables, you can also have something called as the superheated steam tables. This particular table, which has actually been taken out of Felder-Rousseau textbook, is a superheated steam table. What you have here is information about any temperature and pressure, which means the water can actually exist either as liquid or vapor and does not have to be in the saturated condition. So, what you observe in this table is the first column, which is given in the left hand side, is the pressure, and within the brackets below every pressure you have a temperature value which is given, which is the boiling point of water at that particular pressure. And then the next two columns represent the saturated liquid and saturated steam, where you have been given the specific enthalpy, specific internal energy and specific volume for the saturated steam and water. After the temperatures which have been given are all different temperatures not corresponding to the saturation temperature. So, for example, if you were to take the third data point for pressure, which is 0.5 bar, you have a saturation temperature or boiling point given as 81.3 degrees Celsius. So, if you have 0.5 bar and 81.3 degrees Celsius, then you have a point on the vapor liquid equilibrium. So, the values for H cap, U cap and V cap can be obtained from the saturated water and saturated steam values given in the columns here. So, these would be the saturated water and steam values. However, if you want it at a temperature other than 81.3 degrees Celsius, then you can look up this table where you have values for 50, 75, 100, 150 and so on. So, what you would have here is the value for the specific internal energy, enthalpy and specific volume at 50 degrees Celsius is given here, whereas you have 150 degrees Celsius values given here. What you would observe is at 50 degrees Celsius this water exists only as a liquid, it is not in any kind of equilibrium, and at 75 degrees Celsius it will again exist only as a liquid, and at 150 degrees Celsius it will exist only as vapor. So, whatever conditions in which water exists only as liquid is covered within this step shaped box. Everything outside of the step shaped box is a vapor condition. So, within the box you have only liquid existing, it is either called a subcooled liquid or liquid, and outside of it is called the superheated steam, where you have only steam and it is not in equilibrium with anything. So, now that we have looked at these tables, let us see if we can use them to perform some calculations. I strongly recommend that you have access to these steam tables. There are many steam tables which are readily available for either for purchase or for even freely available online. Please use these steam tables, get familiarized with how to refer to these steam tables to identify specific enthalpy, specific internal energies and specific volumes, so that we can make calculations involving steam simpler. Here are some example problems which will help us understand this better. Determine the following of water at 300 degrees Celsius and 10 bar relative to water at 200 degrees Celsius and 60 bar. Specific volume, specific enthalpy and specific internal energy. You have also been asked to identify what phase the water is in for both states and find the dew points for the superheated state. What I have done here is taken out the relevant portion of the steam tables for performing the calculations. The values we have here is pressure in bar and the saturation temperature in degrees Celsius. This is saturated water values and this is saturated steam values, and this is for 50 degrees Celsius, 75 degrees Celsius, 100 degrees Celsius, 150 degrees Celsius, 200 degrees Celsius, 250 degrees Celsius and 300 degrees Celsius. Now, let us look at the values we have, and we have a condition, the final condition is 300 degrees Celsius and 10 bar. So, 10 bar is the value given here and 300 degrees Celsius would be this particular column. So, we have for this H cap is given as 3052 kilojoules per kilogram and U cap is given as 2794 kilojoules per kilogram and V cap is given as 0.258 meter cube per kilogram. So, these lines that you see here are actually the boundaries of the step shaped box which we saw earlier. So, this particular point lies outside the step shaped box, indicating that this would be a superheated steam. So, the condition here is superheated steam. So, the other condition was 200 degrees Celsius and 60 bar. So, this is the 60 bar column and we are trying to find the information for 200 degrees Celsius, which is here. So, we have H cap value as 854.2 kilojoules per kilogram and U cap value is 847.3 kilojoules per kilogram and V cap value is 0.00115 meter cube per kilogram. So, here again this would be the boundary for the step shaped box. So, this value lies within the step shaped box, indicating this to be a subcooled liquid. So, with this we have the information for specific internal energy and specific enthalpy for both these states. Now, we need to find the difference between the two to actually calculate the specific enthalpy, internal energy and specific volumes relative to reference state 1. So, now let us go ahead and do the calculation, but before that let us look at these values and try to get some physical meaning and understanding of what these values are. If you look at the values for internal energy and enthalpy for 300 degrees Celsius and 10 bar, you would see that the difference between enthalpy and internal energy is significantly large. However, if you were to compare the internal energy and specific enthalpy values for 200 degrees Celsius and 60 bar, the value difference is reasonably small. This is because for 200 degrees Celsius and 60 bar, you have water existing as a subcooled liquid. This means the specific volume value is very small, thereby your PV cap value is also small. Hence, your internal energy and specific enthalpy values are not that very different. The percentage difference is actually less than 1%. However, if you were to look at the value difference in specific internal energy versus specific enthalpy for 300 degrees Celsius and 10 bar, it is quite significant, it is more than 10% difference. So, this indicates that the specific volume of steam, which is much higher than the specific volume of liquid water, influences the change in enthalpy. So, this is an aspect which we need to understand and which we can appreciate directly by looking at these values from the steam tables. Let us perform the calculations for finding the difference, so that we will get the answers required by the problem. Delta V cap would be equal to the difference between the specific volumes. So, that would be 0.258, which is the final condition, minus from here 0.00115 meter cube per kilogram, giving you a value of 0.257 meter cube per kilogram. So, this would be the value. So, we have delta U cap as 2794 minus 847.3 kilojoules per kilogram, giving you a value of 1946.7 kilojoules per kilogram, and your delta H cap would be equal to 3052 minus 854.2 kilojoules per kilogram, which is equal to 2197.8 kilojoules per kilogram. In addition to all this, we have also been asked to find the dew point or the boiling point for the superheated steam. So, dew point would be the point at which condensation happens. So, here the superheated steam state is 300 degrees Celsius and 10 bar. So, going back to this values here, you can find the boiling point as 179.9 degrees Celsius, which is also the dew point or the point at which condensation would happen. With this, we have identified all the values that have been asked for, and we have come to the end of today's lecture on introduction to energy balances. In the next lecture, we will look at some example problems and perform tutorial problems to strengthen our fundamentals on how to perform energy balance calculations for simple systems that we have looked at till now. Until then, thank you and goodbye.